So far we have discussed up to chapter number 4. So in this lecture we will start chapter number 5. So the first step on the finite element analysis is convert the strong form into a weak form, and say for elliptical equation, this is the weak form we will get. And once we get this weak form, what we will do is we will assume an equation, a function for u and w, okay, and then we choose that function such that it satisfies this equation, right? And in order to choose that function, what we do is we assume some basis functions. We assume it for both u as well as w, okay. And once we assume it, what we say is u is actually a linear combination of those basis functions. Otherwise it's the u is in the span of the basis function, okay. And we do the same for w as well, okay. And if we assume it like this, then this is how the equation will look like, where this n of x, which could be n1, n2, n3, and here they have limited up to 3 functions, but we could also have many more functions. Fine. And w represents the coefficients which are corresponding to this n1. By the way, these n functions are also known as shape functions, okay. So here this n of x represents a vector, okay, which represents a column vector of n1, n2, and row vector of n1, n2, and n3. And this w represents a column vector of w1, w2, w3. And this dot product between n and w, okay, which will give me this w, and similarly I will have a function for u as well, okay. So this is how I am approximating this w. So this is the this is to denote the approximated w, and this is to denote the approximated u, okay. Fine. So now if you look at this equation, you could see that there is a transpose, right? And you could see those things over here as well as over here, okay. Now what is this? Is it a matrix? Actually it is not. It is w is a function. The derivative of w with respect to x is also a function, okay, and the transpose of that function will once again give the same function. So therefore it doesn't matter whether we put transpose here or not. It's not going to change the meaning of this equation, right? Nevertheless, we put this one because later it will be useful, okay. Now what we will do is we will put this one, okay, in the place of w, and put this one in the place of u. So remember, we have to put this one not just here, we have to put it over here as well as over here, okay. And since we are putting this w in the form of transpose, so this w is equal to this, and w transpose is equal to w, okay. So the transpose of this is equal to, this whole thing is equal to w transpose into n transpose, okay. So that's what I have to put it over here, and if I put it over here, then W is just some numbers, okay, the vector, but it contains some numbers. The elements are some numbers, where this is a vector which contains functions, okay, which is a function of x. Therefore, when I substitute it over here, only this n will get differentiated due to this x, and w is just a constant. So the way I could write this dw by dx transpose as w transpose into dn by dx of transpose. Okay, that's how we can write this term when I substitute this one. Okay, we will have w transpose dn by dx transpose, and if I put this one over here, then I will get dn by dx into d, this d, okay, because d is again just a number, and only this shape function is going to be a function of x. Okay, and I will do this one for this entire equation. I will substitute wherever I find w and u. Okay, fine. And once I do that, solving for u is nothing but identifying what is this d. Okay, so now you could wonder, is it necessary that this n of x for w and this n of x for u has to be same? It's not necessary, okay, but that's one method, and this is a method which has been suggested by Gallatin. Okay, so if we follow his method, then we'll be using the same shape function for both w and u. Fine. Right. Next, what we do is, also we have seen in the last chapter that we will do this integration not for the entire domain, but before that what we will do is we will discretize this domain into subdomains, and then we will do the integration for each domain and sum it over to calculate this integral for the entire domain, right? So if we do that, I have to assume all these things, okay, not for the entire domain but for each element. Okay, and if I do that, this is what I will get. If I do that, this is what I will get, and in this equation, instead of w I have put we, and instead of u we have put ue. Okay, and this is valid for a single element, and that has been summed for all the elements. Okay, and this total thing has to be equal to 0. That comes from our weak form. Okay, so what is this ue, we? Ue is nothing but ne into de, where this ne represents the shape function for that element. Okay, and de is the degrees of freedom for that element. Okay, so which is basically the nodal values of this u. Fine, and the same thing for w as well. And now since we have to use this due by dx, when I substitute this over in the place of u, then I will get dne by dx into de, right, because de is just a constant, and this dne by dx is what we represent it as be, a B matrix. Actually here it is just a vector, but generally it's been called as B matrix. Okay, so in the place of this due by dx, I will put this one, and in the place of this I will put this one. Okay, and in the place of this and this I will put this one. Okay, and if I do all those things, what will I get is this form. Okay, and in this one I am going to accept this dE, the remaining term, okay, including this integration, because it doesn't matter whether I include this dE inside the integral or outside, because this is just a constant, so I can take it out. Okay, once I take it out, and the remaining thing along with the integration, which I am going to call as KE, okay, and similarly this whole thing, okay, I am going to call as F omega E. Okay, and this one I am going to call as F gamma E. So all these things are valid for that particular element. Okay, so here whatever we are doing is for that element, and we have to do the same for all the element in order to make this summation. Okay, fine. So so once I have, okay, but before that I will tell you the names which are used for representing this KE and these things. This KE represents element stiffness matrix. Okay, so because this is a stiffness matrix, you will get a matrix. Actually, this is not a scalar, this is a matrix. Okay, because A and E are just a scalar, but B is a vector. Okay, that's a column vector. Okay, so B transpose becomes a row vector. A row vector into column vector will give us a matrix. So this KE is a matrix and D is a column vector, and this is the degree of freedom of that elements, okay, are the element node values, and this is a element stiffness matrix, and this is a force vector which is due to the body force. So therefore this is also been called as a volume force. Okay, sorry, and then this is a vector which is known as surface force. Okay, fine. So so far it's fine, and we could calculate this for each element, but how to do this summation, right? So that's what we will see next. Okay, yeah, so this is element stiffness matrix, and the sum of this one and this one are the external force. So this is known as external force matrix and force vector. Okay, but while summing it, okay, what we have to do is we have to kind of assemble it. Okay, we have to assemble it in a proper manner. Okay, and that assembling will be performed using this operator, which is known as assembling operator or scatter operator. Okay, so what is this LE? Actually this LE is defined such that this dE is the degree of freedom of the element, okay, and D is the degree of freedom of that entire domain. Okay, this is the degrees of freedom which I have defined for locally and our local coordinate system, which is valid only for the element, and this is for a global. Okay, because sometimes the reason we have such a we are writing this in such a manner is because if we have this DE, then I could use this DE separately without worrying about what is the node number for that corresponding element, right? So without worrying about that, I could perform this integration, and once I perform this integration, then I will use this assembly matrix or the scatter operator and map it to this global node number. Okay, so that's why I'm using this. So since DE is equal to LE into D, so in the place of DE I will use that equation. So if I do that, I will get this one. Okay, and I'll get totally in this form, because I have to do the same for this W as well. Okay, even this W is represented for in this equation is given for element. I have to map it for this entire domain. Okay, and if I do that, there will be one more term of LE, which is this. Okay, and we will also observe a term over here. So finally this weak form, I have got it into this form. Okay, and this is the equation I have to solve in order to identify what is this D. So from this D is what I want to identify. Okay, now how am I going to calculate it further? So if you see in this equation, this W of t, which is the value of W1, W2, W3, which we have seen over here, right? So the weak form is valid, but this equation has to be valid for any value of W. Okay, so any linear combination of this W function, the basis function of W, has to satisfy this weak form. Okay, so which means this vector can take any arbitrary element values. If that has to be satisfied, then the only possibility to satisfy this equation, to have any arbitrary value, the only possible way is making whatever inside this bracket goes to 0. Okay, so from that, what we will get is this minus this is equal to 0. Okay, so and before writing that, what we're going to do is we are going to call this one this first term except this D, the global degrees of freedom, except that if I consider this one, and that's matrix, and we are going to call that matrix as a global stiffness matrix. This is actually, the KE is a local stiffness matrix. This entire thing is a global stiffness matrix, which is represented in this manner. Okay, and this whole thing is a global force vector. Okay, so if I write this equation, I'll write it like this, and this has to be valid for any W. Okay, and that will provide me the equation that K into D is equal to F. Okay, so that is the equation I have to solve. Fine. Now the problem in solving that equation is, so if you see it is like a set of system of linear equations, right, and I have to solve. But the problem in solving is d is the nodal values of u and f is the force vector. But after we apply the boundary condition, what we know is we know the value, some of the values of this this d vector, and we know the remaining values for the f vector. By that I mean, say for one node we either know f, the element of f or the element of d. Okay, it will be mixed. Okay, so some of the d's are elements of d's are unknown and some of the elements of f are unknown, and with that mixed unknowns we have to solve. How are we going to solve? So we are going to solve by considering this thing as r. We call that as a residual. Okay, and so this w transpose r, which comes from this equation, that has to be equal to 0. And one more thing, the condition which is imposed on w is that wherever I have defined the Dirichlet boundary condition, at that place the w has to vanish, right? So let's assume we have 3 nodes. Okay, 3 node problem, and at first node I know what is the displacement. Okay, I have defined the Dirichlet boundary condition. So at that time, for that corresponding node, my w value is going to be 0. Okay, so with that, if I include this condition, then this equation gonna give me this equation. Okay, actually there will be w1 plus r1, but we have imposed this w1 is equal to 0, therefore we are having only the remaining terms. So summing the remaining terms goes to 0. Okay, fine. So now the only way, and if you see here, this w2 and w3 can have any arbitrary value. So if it can have any arbitrary value, then this r2 and r3 has to be 0. Only then this equation can get satisfied. Okay, so with that, if I write this equation, then I will have it in this form. Okay, and this k11, k12, all that thing I have obtained by this by doing all these integrations and assembling. Okay, and the same goes for this one as well. And here if you see, u1 bar is a known value. Okay, u2 and u3 are unknown. Fine. Now what I'm going to do is I'm going to take this. So here if you see, if I know the displacement at this node, I actually do not know the force at this node. This is just a contribution we will get from the body force, but we do not know the contribution from the surface force. Okay, so we know only this one, and we do not know the entire force corresponding to that node. Okay, now if I take this vector and put it over here, I will get it into this form. Okay, so now you could see that the first node I know the displacement, but I do not know this r1. Okay, something I have to add to make it complete, to to identify what is the total force acting on that particular node. Okay, something I do not know. Okay, and here I do not know what is u2, I do not know what is u3 as well, but I know what is f2 and f3. Fine. So how am I going to solve? I am going to solve using the following procedure. So I am just going to consider a matrix corresponding to the unknown displacements. Okay, so this is the known displacement, so I am going to omit that part. Okay, and then I am going to consider the remaining to this equation, okay, which is actually k12 into u1 bar plus k22 into u2 plus k23 into u3, which is equal to f2, and similarly the other equation. And if I consider those two equations and I do some rearrangement, I will get the equation in this form. Okay, and once I get this equation, then if you see, these things are known. Okay, so this is a part of the elements of global stiffness matrix which is known. Okay, and these things are unknown, this is known, and this is also known. Okay, so the only unknowns are u2 and u3, which we can solve using this equation. And once I calculate u2 and u3, okay, then I could use this first equation, which is k11 into u1 bar plus k12 into u2 plus k13 into u3, which is equal to f1 plus r1. So the only thing is only unknown is r1, so that I could calculate, okay, which is this equation. Okay, here if you see, everything is known, and like that once I calculate, I also know what is the force at node 1. Okay, so this is how we calculate the nodal values for u, okay, and some forces at the nodal values as well. Okay, and now what is the solution? So I know now I know what is u1, what is u2, what is u3. Okay, now what is the solution, which is u, right? And the solution is this one or this one. Okay, so u1 into n1 plus u2 into n2 plus u3 into n3. So that's our solution. So this is how we need to calculate or we need to solve a given PDE using finite element method. Okay, thank you.